Today we are going to explore the implicit function theorem, which is a fundamental result in multivariable calculus that tells us when and how we can solve equations where variables are tangled together rather than neatly isolated. Often, we encounter relationships where a function of multiple variables is set equal to 0, such as an equation containing both x and y, where y cannot easily be written explicitly as a function of x. For instance, consider the equation describing a circle where x squared plus y squared minus 1 equals 0. At many points on this circle, we can think of y as an implicit function of x. The implicit function theorem provides the exact mathematical conditions under which such an implicit function locally exists, and it gives us a direct way to find its derivative without needing to solve for the variable explicitly. Formally stated, suppose we have a continuously differentiable function, f of several variables, such as x and y, and we have a specific point x0, comma 0, where the function evaluates to 0, and the partial derivative of f with respect to y evaluated at that point is not equal to 0. The implicit function theorem guarantees that in a small neighborhood around x0, there exists a unique differentiable function, y equals g of x, such that f of x and g of x equals 0, and furthermore, the derivative of g with respect to x can be calculated directly using partial derivatives as the negative fraction, where the numerator is the partial derivative of f with respect to x, and the denominator is the partial derivative of f with respect to y, both evaluated at our point. Let us look at a concrete mathematical example to see how this theorem works in practice. Suppose we have the equation x squared plus y squared minus 25 equals 0, which represents a circle of radius 5. Let us test the point 3, 4, which satisfies the equation because 3 squared plus 4 squared minus 25 equals 9 plus 16 minus 25, which equals 0. We want to find the derivative of y with respect to x at this point without solving for y explicitly. First, we define our function f of x and y as x squared plus y squared minus 25. Next, we compute the partial derivatives. The partial derivative of f with respect to x is 2 times x, which evaluated at the point 3, 4, gives 2 times 3, or 6. The partial derivative of f with respect to y is 2 times y, which evaluated at our point gives 2 times 4, or 8. Because the partial derivative with respect to y is 8, which is not equal to 0, the implicit function theorem guarantees that y can be locally viewed as a function of x. Applying our formula, the derivative of y with respect to x is the negative fraction of 6 over 8, which simplifies to negative 3/4. If we check this by solving the circle equation explicitly for y, we get y equals the positive square root of 25 minus x squared. Taking the derivative of this explicit function using the chain rule gives 1/2 times the square root of 25 minus x squared in the denominator, multiplied by the inner derivative of negative 2 times x, which simplifies to negative x over the square root of 25 minus x squared. When we substitute x equals 3 into this explicit derivative, we get negative 3 divided by the square root of 25 minus 9, which is negative 3 divided by the square root of 16, or negative 3/4, matching our implicit result perfectly. Let us consider a second, more complex example involving 3 variables. Suppose we have an equation in 3 variables, x cubed plus y cubed plus z cubed minus 3 times x times z equals 0. We want to find the partial derivative of z with respect to x at the point 1, 1. First, let us verify that this point satisfies the equation, yielding 1 cubed plus 1 cubed plus 1 cubed minus 3 times 1 times 1 times 1 times 1, which equals 1 plus 1 plus 1 minus 3, or 0. We define our function f of x, y, and z as x cubed plus y cubed plus z cubed minus 3 times I times y times z. To find the partial derivative of z with respect to x implicitly, we take the negative ratio of the partial derivative of f with respect to x divided by the partial derivative of f with respect to z. The partial derivative of f with respect to x is 3 times x squared minus 3 times y evaluated at the point 1, 1, 1, 1 gives 3 times 1 squared minus 3 times 1, or 3 minus 3, which equals 0. The partial derivative of f with respect to z is 3 times z squared minus 3 times y, which evaluated at our point gives 3 times 1 squared minus 3 times 1, or 0. Wait, notice that the denominator is 0 in this specific case, which means the hypotheses of the implicit function theorem fail at this exact point because the tangent plane becomes vertical, meaning z cannot be expressed as a local function of x in a neighborhood of this symmetric point. Let us try another valid point on that same surface, such as the point 2, negative 1, 1. Let us verify the equation. 2 cubed is 8, negative 1 cubed is negative 1 cubed is 1, and negative 3 times 2 times negative 1 times 1 is 6, giving 8 minus 1 plus 1 plus 6, which equals 14. So that point does not satisfy it. Instead, let us test the point 1, 2, 3. Or let us use a simpler function, such as x squared plus y squared plus z squared minus 14 equals 0. Evaluated at the point 1, 2, 3, where 1 squared plus 2, 3, where 1 squared plus 2 squared plus 3 squared equals 1 plus 4 plus 9, which equals 14. Let us find the partial derivative of z with respect to x for this sphere equation. The function is f of x, y, and z equals x squared plus y squared plus z squared minus 14. The partial derivative with respect to x is 2 times x, evaluating to 2 times 1, or 2. The partial derivative with respect to z is 2 times z, evaluating to 2 times 3, or 6. Applying the implicit function theorem formula, the partial derivative of z with respect to x is the negative fraction of 2 over 6, which simplifies to negative 1/3. This demonstrates how the implicit function theorem provides a powerful and systematic way to extract rates of change from complex equations without the need for cumbersome algebraic isolation.